So now we'll start off with question number 7. An infinitely long wire carries current into the plane of the paper. The loop is in the plane of the paper and symmetrically kept with reference to the wire. Loop carries current I2. We have to find which of these options is correct. So we have an infinitely long wire.
Yes.
That is carrying its current into the plane.
Yes.
So, and we are given a loop ABCD, which is in the plane of the paper and is symmetric from the point of the
yes, it is symmetric.
which would take it as the wire.
Yeah.
So this other loop is carrying a current I2. So we're given 4 options where the net force on loop is 0, the net torque on loop is 0, or owing to the account of torque, the loop rotates clockwise or anti-clockwise. So can you tell us how do we approach this question?
Yeah, first let's for simplicity, let's understand how this loop is oriented. So if we look from O,
Right.
what we'll see is that this is the wire, the infinite wire, which is going into the plane of the paper.
Alright.
And here we'll see the loop, because like this is in the plane of the paper, all this loop, and this is into the plane of the paper.
Okay.
So this whole loop will be represented like a line. Now let's see how we'll solve it or go about solving it.
Right.
So there are 2 things basically which are asked. First is the net force on the loop and the net torque on the loop.
Okay.
So for force, let's see, we'll consider all the 4 segments which are BC, CD, DA and AB,
Right.
and then sum all the forces on these particular segments.
Okay.
So if we see that for BA and CD, it is it is basically in the direction, or whatever current element we take here, loop
Okay.
element DL, that will be in the direction of the magnetic field. Because see, this is a circular with respect to the wire, with the center lying on the wire.
Okay.
So basically the magnetic field will come around to be like this, and this, and for here also it will be like this, in the particular direction CD or BA.
So can you tell us how you found the direction of the magnetic field here?
We found it by the right hand rule.
Okay.
Keep the thumb in the direction into the plane,
Okay.
and when we curl our fingers, they will come in a loop around BA,
Okay.
in the direction of BA.
Right.
So basically we see that because it is in the direction and the force is V cross B whole into Q. So this V cross B equals V into B into sine theta. Theta
Okay.
here is 0, so the whole force on BA or CD will be 0.
Right.
Now let's consider for BC and AD.
Okay.
Now for BC the current is here, and for AD the current is going here.
Alright.
Okay. And let's look at the direction of the force. The direction of the magnetic field. Here, let's consider this BC, and here it's AD.
Right.
So the direction will be, because in BA it was in the direction of BA, so the magnetic field will be like this,
Okay.
perpendicular, and for here it will be like this. But the current here is flowing in this direction, and here the current is flowing in this direction.
Right.
So basically the sum of the forces on these will equal 0, because force on here will be equal to force on this one, force on AD equals force on BC,
G.
but the directions will be opposite, so they'll cancel.
Okay.
Hence finally find that the force or net force on BCDA will be 0.
Right. So we are taking the segments over here. First we take the segment AB and CD on which the force is 0.
Yes.
And again when we consider the segments BC and AD, they add up to 0 summation on the account of being the force being equal
Yes,
and opposite,
exactly,
right?
Exactly.
Okay.
Now let's consider torque. So see, for torque also we can do the same thing. Like we can consider a particular segments
Right.
and find the force on them.
Okay.
So basically we found that the force was 0, but in the case of BC, see, this is coming here perpendicularly, okay, and this is the magnetic field, this is the current I. In the direction we take DL, so basically the force will be I into L cross B. L is here,
Right.
B is here. We do the cross product, it comes out of the plane.
Okay.
So basically this force is acting out of the plane,
Alright.
and for AD the force will be acting into the plane.
Okay.
Hence because of this a torque will be formed which will rotate BC out of the plane and AD into the plane. And when we view it from O, the motion will be clockwise because see it is coming out, so this will rotate here.
Alright.
So going back to the options and seeing which ones are true. The net force on the loop is 0. This is correct.
Okay.
And C, loop rotates clockwise about O dash when seen from O.
So we are considering it from the point of view of where the wire is placed, right?
Yes, yes.
So, okay, fine. So this was a question. We had an infinitely long wire carrying current in the plane of the paper. There's a loop ABCD kept in the plane of the paper and symmetrically with reference to the wire. So we had to find out the force and the torque on the loop owing to the magnetic field generated by the wire, right?
Yes, yes.
So we divide into segments. We first look at the loop and the magnetic field acting on it. We divide the whole loop into 4 different segments.
Yes,
and in the beginning we'll see that the net force on segments BC and AD on the account of this is
Yeah, net force. The net force on BC equals the net force on AD, but
Right.
they are in opposite direction. So
Okay.
summing them up equals 0.
the summation adds up to 0, and AB and CD the force becomes 0
Yeah,
here
force
again.
is 0 because
And-
the magnetic field is in the direction of the current.
Right. So and then we go about finding out the torque acting on the segments, right?
Yes, yes.
Which these are the segments AD and BC.
Yeah.
Right. So how do you go about this again? Could you just explain the
Basically, we had BC
Right.
and the current was coming here, and earlier we saw that one force will be acting on this and another force will be acting on AD in the opposite direction.
right?
So what this means basically is that it will generate a couple,
Okay.
so that the force will act upwards on BC and into the plane on AD.
Right.
So this will result in a torque about O dash
right.
in viewing from this axis, and from O it basically then rotates in the clockwise direction.
Right. So we look at a couple that's generated due to the
Yes.
field, and hence the loop rotates clockwise.
Yeah.
All right. So that was question number 7 for us. We'll start off with question number 8 now. 2 parallel wires in the plane of the paper are a distance x0 apart. A point charge is moving at a speed u between the wires in the same plane at a distance x1 from one of the wires. When the wires carry current of magnitude I in the same direction, the radius of curvature of the path of the point charge is r1. In contrast, if the currents I in the 2 wires have directions opposite to each other, the radius of curvature of the path is r2. If x0 by x1 is equal to 3, then r1 by r2 is what? Right? So the question basically asks that there are like 2 parallel wires that are put in the plane of the paper, which are separated by a distance x0, and the point charge is moving at the speed u between the wires at a distance of x1 from one of the wires. So we have 2 cases here basically. When the wires carry current of magnitude I in the same direction, we have the given radius of curvature of the point charge, which is r1. On the other hand, in the second case, if the current is I in opposite directions, the radius of curvature of the path is r2. So we are given the ratio of x0 by x1, which is 3, and we have to find out r1 by r2. So can you please tell us how do we go about solving this question?
First we see about the radius of curvature.
Right.
Basically we try to figure out the trajectory of the particle
All right.
as to why it will move in the circle and why it will have a radius of curvature.
Correct.
So for that, let's see that if a particle has a velocity v
Right.
with a perpendicular and there is a perpendicular magnetic field b,
Okay.
so it is just thrown with velocity v with a perpendicular b.
Right.
So a force acts on it, q into v vector
Okay.
cross b vector.
Right.
So v cross b. So if we do the cross product, basically it will come into the plane, and the particle, like if we watch from here,
Right.
this is the I, the movement the movement will be like somewhat like this in a circle.
Okay.
So basically this is into the plane because the force is acting into the plane.
Right.
So like it will start off from here, it will go down, make a circle, and then come back up here again.
Okay.
And the process will continue.
Right.
So this is basically because a perpendicular magnetic field acts on it. Now let us see the radius of curvature of this circular track traveled by the particle.
Okay.
So we know that whenever a particle travels in a circular path, there is a centripetal force acting on it inside, which is equal to mv square divided by the radius. Now this is derived by kinematics, so
Right.
there has to be a force which provides this centripetal force.
Okay.
And in our case, this force happens to be the magnetic force, which is perpendicular to the velocity of the particle.
Right.
Since v cross b is v into b into sine theta, theta here is 90 degree, we can just write q into v into b.
Okay.
So v cancels, basically we get r equals mv divided by qb.
Okay, so this is the radius of curvature for the charge that's traveling in a circle,
Yeah.
right? All right.
Even the we have a perpendicular magnetic field associated with that.
Right.
Now we see how this applies to our case.
Okay.
So let's say there are two wires carrying a particular current,
Right.
say I, and there's a charged particle moving in the plane of the paper
Okay.
with some velocity u.
G.
So this is basically all three are in the plane of the paper.
Right.
Now the magnetic field, because of this, on a particular point, say here, at which the particle is,
Okay.
will be in this particular case, it will be into the plane of the paper,
Okay.
and for this it will be above the plane of the paper. So
okay,
the
so
net,
it's going perpendicular into the paper and one is coming out of the paper,
yeah,
right?
and
Okay.
there's some because we superimpose magnetic fields to find the field at a particular point.
Right.
So there's some will basically be either up, that is perpendicular to the plane of the paper,
Right.
either up or down.
All right.
So we have the same case here, like there is a v, which is a u, and perpendicular to this there is a b.
Okay.
So the particle will move in a radius of curvature, which
Alright.
for our case can be given by mu divided by q b. Now let's look at the various b, because in the cases
Right.
which we have this fixed, and when the current changes, then b is the only one that changes.
Okay.
So for case 1, we have this, say this is in the same direction and these are at x0, and here is a particle. This one is, say, x0, this is capital X0 by 3, and this much will be 2x0 by 3.
All right. So how did we arrive at this? Could you just?
Yeah, it's basically given in the question, because you see two parallel wires are they are at a distance x0,
Okay.
and then the distance of the charge from one of them is right x1,
Okay.
and
right.
x0 equals 3x1
Right.
as given. So basically this x0 by 3 will be our x1, and the remaining part is 2x0 by 3.
Right.
So let's see the magnetic force at a particular point, say this, which we considered. Because of this it will be into the plane of the paper, and because of this wire it will be above the plane of the paper.
All right.
So when we find the net magnetic field, it will come into the plane of the paper,
Correct.
and it will be a difference of the magnetic field because of this wire and because of this wire. So let's find that out.
Right.
Mu naught I by 2 pi 1 by d1 minus 1 by d2. So it basically comes out to be mu naught I by 2 pi 1 divided by x naught by 3 minus 1 divided by 2x naught by 3.
Alright.
So let's call this field to be B1, which is equal to, let's simplify it further, mu naught I by 2 pi. 3 will go up, so it will be 3 by 2 x naught. Okay.
Alright.
Now let's consider our case 2. In that case, like, we can just see that because the currents are opposite,
Okay.
so because of this it will be into the field, into the plane of the paper, and because of this also the field will be into the plane of the paper.
Right.
So we can just, like, instead of a minus sign here, there has to be a plus sign. We'll just add them up.
Okay.
So it will be mu naught I by 2 pi,
Right.
1 divided by x naught by 3 plus 1 divided by 2 x naught by 3
Right.
will come out to be mu naught I by 2 pi whole into 3 by x naught plus 3 by 2 x naught, which equals mu naught I by 2 pi 9 by 2 x naught.
Alright.
Okay. So now we relate this. We've seen that these are the magnetic fields B2,
Okay.
and previously we saw that the formula of the radius of curvature is directly proportional, is mv by qb. So because the mass is same, because it's the same particle, velocity is u, charge is same, so we can, like, directly say that r is directly proportional to 1 by b.
Okay.
Like, these sort of analogies or these sort of relations are very important because they can help us in finding out the answer directly with little calculations here.
Right.
Because, like, we could have just found out the r for various b1 and b2, but here we just find out the relation,
Right.
and hence we derive at this that r1 by r2 should be equal to b2 by b1. So we do b2 by b1 and we find the answer will come out to be 3.
Okay. So that was the solution to our question number 8, where we were supposed to find the ratio of the radius of curvature of the path of the charged particle. So to start off with, we looked at defining the concept of radius of curvature, which is the radius of the circular path in which the charged particle moves in the magnetic field. So we have the formula R is equal to mv divided by qv, and then we look at the two different cases we have, wherein in the first case the current in the two parallel wires are flowing in the same direction, and we look at the field exerted on the account of the wires by the superposition principle. Right. So we have B1 from that, and in the second case we have currents flowing in the opposite direction, and with this we find
the magnetic fields add up.
Right. The magnetic fields here add up as they are in the same direction, so we get B2, and then we derive an important relation where we find out that R, the radius of curvature of the path in a magnetic field, is inversely proportional to the magnetic field. Right. So we get R1 by R2 is equal to B2 by V1, and since we have already derived the values of B1 and B2, we apply this and use it to get the ratio of R1 by R2, which comes out to be 3.
Yeah, and just a word of caution here that here the particle was the same one. That's why we could actually use it. R1 by R2 equals B2 by B1.
Right.
Say if there were two different particles we had to compare. In that case, R1 by R2 would have been B2 into Q2.
Right.
Divided by Q1 whole into M1 V1 by M2 V2.
Right.
We had to go strictly by the formula, but since M, Q and V will cancel out, this gives the relation.
Okay. So that was the solution to question number 8.